right, good morning, everybody. Hopefully you're ready for another exciting morning of chemistry with your host, me, Dr. White. Quick commercial from Dr. White. If you look over here on Blackboard, you see Dr. White's Chem 1105 YouTube channel. I'm pretty much up to date. I still have a few early lectures to get up there, but if you want to see me again, or if you happen to not be clear about something, always feel free first to ask me in person, but don't forget you can also see me on YouTube. I'm talking about solutions. Remember, solutions are a mixture where you have two chemicals or substances mixed together and neither react, and it's homogeneous, which means it's the same throughout. And anybody drive by a gas station and think about the fact that they're selling mixtures or solution? That's gasoline is a very complex one. I think I mentioned that the other day. And if you think about the air you're breathing as a solution, I believe on Monday I finished up, I was starting to talk about solubility, and the last slide I talked about was this one. And is my memory good? What? All right. You never know when your hair starts getting gray. Thank God, not me yet. Hopefully never. Anyways, back to chemistry. All right, we're talking about solubility. Remember, solvent, the component of a solution present in the greatest amount. Solute or solutes, the other components. So we're talking about solubility of a solute in a solvent. Most solutions, but not all, but many, the solvent is water, but it doesn't have to be. And the solubility of a solute is the maximum amount of solute that will dissolve in a given amount of solvent. And what's not up there at a certain temperature, because it is temperature dependent. But let's go back out into the real world. If we go to Wikipedia, by the way, for many years I used to say Wikipedia, and my students would always say, no, it's Wikipedia. They finally trained me. Anyways, what you don't know, but I do, and now you will, is table sugar is called sucrose. It's a molecule. I bet you never thought sugar is a chemical. It is. And a lot of the things you think of, oh, I use this all the time, it's a chemical. And if you look on the right-hand side, under properties, you'll see solubility of water, and here they actually give a temperature at 25 degrees C, which is, I believe, approximately 77 Fahrenheit, which is called room temperature by definition. You'll see that you can dissolve up to 200 grams, and here they have it in 100 milliliters. This is strange. Usually don't see deciliter. That means you can dissolve up to 200 or 2,000 grams in 1 liter water, which is almost a whole pound of sugar in a liter of water. That's sweet. And if we look at the table down below and multiply this by 10 to get liters, and you can dissolve a lot of sugar in water. And that's solubility. Now, the other thing the solubility tells you is you can't put any more in than that. When you're at the solubility of a solute, if I say Compound X, I can only put 100 grams of water in 1 liter. If I try and put 1 molecule more, it won't dissolve. If it's a solid, it will go right to the bottom. We call that a precipitate. So the solubility tells you a lot. Now, switch is on. When we talk about solutions, there are different descriptions or definitions of solutions chemists use. And it turns out these descriptions also have come into our daily language. Now, the first one is a saturated solution. A saturated solution contains the maximum amount of solute that can be dissolved under the conditions at which that solution exists. And when I used to work, when I was a grad student, there was this one solution I used to clean up or work up reactions, as it's called, and that was sodium sulfate solution, and it was easy. You put a lot of sodium sulfate in a bottle of water, you shake it up, and as long as there was salt in the bottom, you knew it was saturated because no more could dissolve. So a saturated solution is a solution that you have the maximum amount. So if I were to ask, can you dissolve any more sodium chloride in a saturated solution of sodium chloride? And the answer is no, because you're at the maximum solubility of that solute. So that's a saturated solution. Now, the next definition I'd like to talk about is a dilute solution. And a dilute solution is a solution that contains a small amount of solute relative to the amount that could dissolve. So if I have a dilute solution of sugar, I just have a tiny, tiny bit of sugar in there. Not a lot, because it's dilute. Oh, by the way, bartenders don't like being told, are you serving a dilute drink? In other words, there wasn't that much alcohol in there. They don't like hearing that. Bartenders don't like hearing chemistry in general, but especially that. So dilute means you have a small amount of solute present in that solution compared to what you could dissolve. Now, the opposite of dilute is concentrated. Now, a concentrated solution is a solution that contains a large amount of solute relative to the amount you could dissolve. In other words, when I say I have a concentrated solution of sulfuric acid, I have almost the amount maximum, but not there. I have a lot of sulfuric acid in that solution. Now, it's not as popular as it used to be, but how many of you are familiar with concentrated orange juice? You know, you get it in a can and it's frozen, and what do? You take that can and you put it in a pitcher or container, and you put water in there to make it a dilute solution. Why is it called concentrated? Because there's a lot of the orange juice without the water in it, a lot of it removed. Now, when I was in college, one of my fraternity brothers loved to eat concentrated orange juice like ice cream. Ugh. Now, different things for different folks, but not my cup of orange juice. Ooh, that was a bad joke even for Dr. White. But anyways, like I said, concentrated things, the name concentrated, if you go in the supermarket, you can see different things. Here's an example. I don't know, let's see if they use that or not. Let's look in the real world. Now here they say condensed, which is another way, but if I were labeling this, I would call it concentrated cream of mushroom soup, because it's got a high amount of the cream of mushroom stuff material, I'm being scientific, and what do you do to cook it? You put in either water or milk to dilute it to make a dilute concentration. No, I wouldn't eat this out of the can. I'm sure it doesn't taste that good. It's too concentrated. But things like this are in our daily life. And if you think about it, soup is a solution, certain types, some are something else. All right, the next thing, which is probably one of the more important things I'll teach you this semester, hint, and that's aqueous solution. Aqueous solution tells you the solvent is water. If I say I have an aqueous solution of salt, the solvent is water. If I tell you I have an aqueous solution of potassium bromide, what's the solvent? Water. Now, how do you show aqueous? When you see in a formula, bracket, AQ, close bracket, that means the solution is aqueous. And that immediately tells you the solvent is water. And that's aqueous. Now the opposite of that is non-aqueous. Non means without, and non-aqueous tells you it's a solution where the solvent is not water. And I hope the gasoline I bought 2 days ago was non-aqueous because I don't want any water in my gasoline. Come winter, that will freeze up my gas line in my car, which luckily in the last number of decades that hasn't been a problem with gasoline, especially since they put ethanol in there because that helps keep the water out of gasoline. So gasoline would be non-aqueous. If you had a cup of tea this morning, like I did, actually I had a mug, it's about this big, like this, I'm a tea drinker, and that was aqueous because it had water in there and the solvent was water. Now, what are some factors that affect solubility? I won't ask this on a test, but you should know for your daily life, what are you trying to dissolve the solute in? If it's not soluble in water, that's going to affect the solubility. Temperature. For most things, when you raise the temperature, things are more soluble. How many of you have ever made a sugar syrup or solution? Dissolving sugar in water. If you're a cook, and by the way, if you're a good organic chemist, you're a good cook. I'm a good organic chemist, so you know what kind of cook I am. And what you do is heat it up a little, and that helps dissolve a large amount of sugar quicker. Now, another thing is, what solute are you trying to dissolve in it? Are there other solutes present? And even what's the pressure? The atmospheric pressure will affect solubility in certain cases. So these are all certain things. The most important one of those is temperature and solvent. They're about equal. And as I just mentioned, the effect of temperature on solubility, the solubility of a substance depends on the temperature of the solution. For most, not all, but most solids, about 99%, solubility increases as temperature increases. The one exception I can think of very quickly is, what was that? That was mine. All right, well, whoever it was, tell my stockbroker, sell that stock. Anyways, was that yours?
No.
We're not being invaded by Martians, are we? Okay, sure. All right, now for most solids, like I said, the solubility increases. The one exception of that is ammonium chloride. The way to get it to be more soluble is cool down the solution. And I had to teach that to someone in the chemical plant. I got a call, is I do consulting. How come we can't get this to dissolve? What is it? Ammonium chloride. Are you heating it? Yes. No, that won't work. And that's one of the few exceptions. All right, switch is on. I've just turned it to 15. If I could only turn the dial to 10, I've turned it to actually 15. All right, now, for most of you, you look around and see two things in each other in a mixture, and you say, oh, look, that's a solution. And the answer is not always. We also have what's called a colloidal dispersion. Now, colloidal dispersion is different. How is it different? It's not true solution. You really don't dissolve one chemical in another. What you have is small particles of one substance dispersed in another. There's still small pieces floating around. And we call that a colloidal dispersion. Sometimes it's abbreviated or shortened to just a colloid. And mixtures in which materials are not dissolved, but dispersed. Now, instead of calling something a solvent or a solute, we use a different term for a colloidal dispersion. And I will never ask on a test, but I put it on the slide. This first phase is the equivalent to solute in a solution. Dispersing media is equivalent to solvent in a solution. But we use different terms in our daily life for colloidal dispersion. Now, this is very important. Unlike solutions, colloids or colloidal dispersions will disperse light. I think that's one reason they call it dispersion. No, not really. Pass through them. Now, what does that mean? This so happens your instructor is a flashlight junkie, and you can tell I have emergency one here. Let's see. Battery's dead. I'll have to change it. Anyways, and then on my key ring I have a couple. So if I had sugar dissolved in here, quick experiment, you don't even need your safety goggles. All right, watch. Oh look, the light goes through. Why is this red? Because it doesn't ruin your night vision if you have to use it at night. And then because I'm a real flashlight junkie, I also have a green one which doesn't ruin your night vision either. Don't ask why, but I do. All right, for a solution, when you have a true solution, it will not disperse light. It will go through. If I had a colloidal dispersion, you would see when I did this nothing on my hand. Why? Because the small particles that are not really dissolved scatter the light and won't let it go through. Now, what's an example? You can try this at home to see if Dr. White's lying to you. I'm not. And that is, you should know what are examples of colloidal dispersions. Milk is a colloidal dispersion. Why? Well, if you take a flashlight and a glass of milk, you won't see light on the other side. Because milk has particles dispersed into water of fat and proteins. And it's pretty well dispersed. Also, it's homogeneous. That's an important part of a colloidal dispersion. Another one is latex paint. If you've ever painted a room, like a bedroom or something like that, I've done that, or in my garage, I painted the inside and other rooms, you'll know it's fun nowadays to use a paint because you're using latex. It dissolves in water to clean up the brushes. That's pretty easy cleanup. Before, they used to use oil-based paints that were not fun to clean up. Now, if you take some paint and you put a flashlight through it, you won't see in it while it's still liquid, not while it's dry. You won't see the light go through. Now, one you probably haven't thought about, but time to, and do not try the flashlight trick at home, is blood. Blood is a colloidal dispersion. It's not a solution. The dispersing media in blood, there's a good thing, is water. But what's going through my blood now, well beyond my knowledge of the human body, but amino acids, proteins maybe, fats and oils are going through, or fatty acids are going through, and they're not dissolved, they're dispersed. And right now, also CO2 and oxygen are going through my blood attached to hemoglobin. Now I'm really getting into beyond my knowledge of the human body. But blood is a colloidal dispersion. Now let's go back to one more product that's a colloidal dispersion. I'll do a couple. I think most of you are familiar with the product you can buy at any grocery store, mayonnaise. Hellman's is the best. But anyways, if you look at mayonnaise, hold it up, you can't see through that. And that's a mixture, a colloidal dispersion of oil and water and a surfactant, which I'll teach you about later in the semester, which is found in an egg, or actually an egg yolk. Bet you never thought of eggs and egg yolks as chemical. They are. Oh, it's getting scary. All right, let's move on. What if I were to ask two of you, just pick at random, go upstairs in our lab, here's some salt, here's some water, make me a salt solution. Would you come back if you were in separate labs with the identical salt solution? And the answer is no. Well, how do we get around that? Well, chemists use the term concentration, and that's how we can quantitatively describe a solution. Quantitatively means how much solute, how much solvent. So if I ask a person, I want this type of solution, no matter who I ask, they'll do the right thing and come back with the right solution. Now, there are three types of ways we describe concentration. One is percent concentration for quantitatively describing it. Sometimes it's called percent by mass concentration. Another way is percent by volume. And then, in my favorite color, but you can't guess what my favorite color is, red.
Red.
Very good. And that is molarity. So these are the three different ways chemists describe and also make solutions. Percent concentration, percent by volume, and molarity. Let's look at percent concentration. Percent concentration, by the way, this formula you won't have to memorize. It'll be on important information on test 3. Speaking about test 3 and important information, remember Friday, I will be going through in lab the gas problem, so I highly recommend before Friday when I do it, you try it. Now, percent concentration, or sometimes called percent by mass, is defined as the mass of the solute, and usually you're trying to find the concentration of one solute, divided by the mass of the solution times 100. Remember, the mass of the solution is equal to the mass of the solute, or solutes if they're more than one, plus the mass of a solvent. All right, let's look at the following, but first, I'm going to mixing some water, which is a chemical too. Wait until everybody's got it written down. For those who can't read my handwriting still, if a solution contains 45 grams of potassium chloride, KCl, 55 grams of water, what is the percent by mass, and I could have written down concentration, of the KCl in this solution? Everybody have it written down? Going once? I think I stole that pencil. Tomorrow at 6 a.m. I'll be giving lessons in speed note-taking. All right, let's take a look at this. First of all, what are you trying to find? Percent mass of KCl. What are you given? This. What do you know? Percent mass equals mass of the solute divided by the mass of the solution times 100. And 100 is an exact number. So if we look at this, here we're trying to find KCl, because that's our, how many grams do we have? 45 grams. Now, what's the mass of the solution? The mass of the solution is the sum of all components in the solution. If I add them together, I cheated so I wouldn't have to use a calculator. The answer is 100. So the mass of solution of this example is 100 times 100. And now let me get out my calculator. And the answer would be 45. Actually, I should have made 101. But for this, I'm not going to do significant figures. 45%. KCl. And that's how you find mass of solution. Now, it turns out mass of solution, I'll do another one in a second, is used in your daily life. You're just not aware of it. So, let's go back to my can of cream of mushroom soup. By the way, I like cream of mushroom soup. I also like onion soup and chicken soup. And some of those I make myself, it's better. And if you look at the ingredients, these are listed in order of percent mass. I bet you didn't know that, but they are. And if you notice, what's the first ingredient? Water. So the most thing in this product, cream of mushroom soup condensed, is water. Then they have mushrooms. Yes, mushrooms you could think of as a mixture of chemicals, or it's chemicals made up in things like protein. I don't think there are any fats and oils, but carbohydrates and mushrooms, those are all chemicals too. Your food is chemicals. I teach that in organic. And then there's these different chemicals. And the very last thing is garlic extract, which is a chemical too. I teach that in organic chemistry. So when you look at any ingredients, let's look at another one. They're different amounts, and they're ordered in list of decreasing percent mass. Can everybody see this right here? Hold on. Through the miracle of a keyboard, you can't. This is Scope mouthwash. And you can buy equivalent, but the Walmart brand is the same and it's half the price, so if you use Scope. Now, being an organic chemist, and remember I told you learn a lot about me? And here, Scope, if you look at what's the first ingredient, it's not ordered in there. Let's see if I can get the label. We come down here, if you look at here, ingredients, and it's in 2 languages, so if you're multilingual, you can understand both. And here, the most important thing, the highest concentration or amount is water, and then alcohol, and I would drink this to get drunk, and then various other chemicals. Now, this has nothing to do with percent concentration, but the cetylpyridinium chloride is a biocide or antibacterial, and it's much better, at least in my mouth, than, what's the other one, Listerine, which uses another molecule as that. And unfortunately, in my family, it runs heredity, due to heredity, bad teeth, and dental problems and gum. And for many years, I was using through one dentist this mouthwash that had a different biocide. That was in a prescription bottle. You had to have a prescription. It was $70 a bottle. And the other thing is, it turned your teeth brown, so you had to keep on brushing with special toothpaste, which was not fun. But it kept my gums. If I didn't do that, I'd be screaming right now in pain. Well, unfortunately, that doctor, because of health reasons, dentist, had to retire. Probably the best dentist I ever had. Eventually, unfortunately, passed away. But in between dentists, my gums were hurting me, and I didn't want to buy another bottle of the prescription. And being an organic chemist, I went and looked at the mouthwashes, because they're biocides, like the one I was using, but not prescription. Tried the Listerine, didn't work. This stuff did, and notice I'm not screaming, because now it keeps my gums nice and fresh. But here, the concentration, you notice they don't put very much because it's almost at the end of the label. All right, let's take a look at this one. And a solution contains 25 grams of sugar and 75 grams of water. What is the percent mass of sugar in this solution? And because I like to share the fun, I'm going to let you have fun and try it on your own first. as always, don't forget on Friday, please be on time, please wear proper clothing. And shoes also. Those who finish early, I ask your patience. I try and give everybody time to finish. The rest of you finish. All right, I think everybody's just about finished. So let's do this. First question is, what are you being asked to find? What's the mass, percent mass sugar? What are you given? Do you have 25 grams sugar, 75 grams water, and now what do you know? Percent mass sugar in this case equals the mass of the solute, in this case mass mass of the solute divided by the mass of the solution times 100. Mass of the sugar is 25 grams sugar. How much is the mass of the solution? The mass of the solution is the sum of all components. And add it up, 100. So I have 100 grams here. Don't forget times 100 because it's percent. And in this case, this is something that would be quite sweet, and it's 25% sugar, which is pretty sweet. And I guess that's Captain Crunch or something like that. That's pretty sweet too. I've had that in decades. All right. That's percent mass. Everybody, listen, switches off. One other one is percent by volume. And percent by volume is equal to the volume of the solute divided by the volume of the solution times 100. The volume of the solution is the sum of all the different components of the solution, usually solute and solvent, and that's how you get percent volume. Why am I not asking you to learn this? Because it's rare where this is used. One of the few places I know where it's used is bottles of wine. And if you look at a bottle of wine, you'll see percent alcohol is by volume. And let's see if I'm lying or not, if I can find something. And if you look at a label of bottled wine, by the way, I worked in Germany. I worked for 2 Anglo-Dutch who had plants and research also in Germany. I got to find that German white wines, in my opinion, is much better than French white wines. They taste like vinegar. But anyways, this is the best, the Pure Sport Golden Trocken, and this is the Spätlese. And if you notice here, it has, I don't know what the number is, 8% by volume of alcohol. That's one of the few places. By the way, I don't get any kickbacks, but Binny's always has a good selection of Pure Sport or Golden Trocken wines, and they have regular Cabernet, which this is a Spätlese. Cabernet is sweet, Spätlese is much sweeter, and Auslese is very sweet, and I like sweet wines. And this is a white wine, and these are always amazing. I've been buying these wines since the mid-'80s. That's a while. I shouldn't have said that. Anyways, that's one of the few places I see percent by volume. And therefore, I'm not going to talk about it anymore, unless you want to go buy a bottle of wine, which I am not implying you should ever consume alcoholic beverages. All right, let's move to the last way of describing concentration. I've just turned the switch. If it goes up to 10, I've turned it up to 50. And that is molarity. Molarity is a unit of concentration of a solution that chemists use. Not only in the lab, we use them in a plant. And the molarity of the solution is designated by a capital M. It is a ratio giving the number of moles of solute per liter of solution. I'll never ask on a test in words, what's the molarity? But you should know, and I'll put this on important information, but you should know. See, I even have it at the bottom. I don't know why these keep on popping up. But molarity is equal to moles of solute per 1 liter of solution. And see, it even says on the slide, very important, know this. And I won't make you memorize this, but you should know how to use this. And molarity is a way of describing concentration. By the way, don't forget the T on the end of important. So look out, it's Bad Humor Wednesday. Really bad. Wow, I better throw another one in. Do I look invisible now? White on white on white. All right. Let's move to the next slide. Has everybody got this down? I see a few smiles out there, some are very bad. Humor wasn't that. Now, most people don't go around with a liter measuring device. What you do measure is milliliters. And 1 liter equals 1,000 milliliters. Therefore, molarity, which is moles per liter, is also equal to moles per 1,000 milliliters. And the most important useful thing is the following. Most important thing for you to remember is molarity, which is abbreviated by a capital M, and I'll show you how that is in a second or two, is equal to moles of solute per 1,000 milliliters of solution. And this is a very important thing. If you go upstairs in our stockroom, upstairs, and some of the chemicals things lab manager puts out, you'll see labels that tell you the molarity, the concentration of those solutions, which is important to know. sometime in the future, if you were to see 3 points each, what does this mean? And you see a number, capital M, and the formula of a compound or substance. And as soon as you see the capital M, what does capital M mean? Molarity. You can put down 1 liter, but you'll find in most of chemistry, 1,000 milliliters works better. And now, what does this mean? You see the capital M, that tells you molarity. The number in front tells you it's 4.76 moles. What's the solute? Sodium chloride per 1,000 milliliters. So what does this mean? This is shorthand that chemists use, molarity. And it's moles per 1,000 milliliters. Now when you see a number with capital M and the solute substance, it tells you how many moles per 1,000 milliliters. Why don't you try this one on your own? What does this mean? I think everybody's done. Let's take a look at this. As soon as you see capital M, that tells you molarity. And what is the molarity? The number here tells you how many moles of a substance per 1,000 milliliters. And therefore, what does this mean? 3.21 times 10 squared moles of H2SO4, sulfuric acid, per 1,000 milliliters. And that's what that means. Oh, let's do one more. ABC, round it off. And why don't you try this one? What does this mean? Can you guys in the back see this okay? You see it? I think everybody's done. Let's take a look at C. And the question is, what does this mean? And we have in C 2.11 capital M C2H6O. I had to sneak this in. What's this compound? Ethanol. What's ethanol? That's the active ingredient in beer, wine, and hard spirits. Not that I'm implying you should ever buy it. And what does this tell us? Capital M, molarity. Moles of solute per 1,000 milliliters. And therefore, we immediately know that is 2.11 moles of ethanol per 1,000 milliliters. And that's molarity. Now, it turns out having molarity, having stock solutions made up either in bottles or in plants, say 5,000 gallons of it, and I've done that where I've helped people, I've supervised making large molar solutions. What's the benefit of that? Well, let me show you. And I have it on the next slide, a number of problems, important molar questions. How many moles of solute are in X milliliters of a known molar solution? So let's do one. And let's look at the following. I could even make it 6 or 7 points or 8 if I'm in a good mood. But anyways, I always try and be in a good mood when I write a test, so it's fair. But let's look at the problem. And I'll decode it in case you haven't figured out my handwriting by now, if you have. How many moles of HCl, that's hydrochloric acid, are in 525 milliliters of a 3.75 capital M HCl solution? So what are we being asked to find? How many moles of HCl? And I'll give you another 32.7 seconds to write it down. All right, let's go through this. The first thing is, what are you being asked to find? Moles of HCl. What are you given? We have 525 milliliters of solution. And you're given this strange number, and with letters too. And the first thing I'm going to do before I go any further and say to myself, what does this mean? And you just practice that. Capital M, molarity, moles per 1,000 milliliters. And what does this mean? 3.75 moles HCl per 1,000 milliliters. And now, really, this is the key number we have, is we had to determine what this was, but we start with this. If you want to close the door, because if I can hear it, you can hear it. But you can hear it down the hall, those people. But anyways, if we could convert it in one ratio, what are we trying to get to? Moles of HCl. But you thought we were done with it. Guess what time it is? It's time to use your good buddy, your good friend, unit analysis. Whatever units I'm trying to get to, go on top. Whatever units I'm trying to get rid of, in this case milliliters, goes on the bottom of this ratio. And now I ask myself, where do I get those numbers? Well, I figured out what this meant. This meant 3.75 moles of HCl per 1,000 milliliters. The 1,000 is a definition, therefore an exact number. And before I pick up my calculator, I'm going to look, do my units cancel out? Now, you don't have to do this longhand, but this first time I'm going to do it. Milliliters times moles HCl divided by milliliters. What happens? Anything divided by itself becomes the number 1. So am I left with the right units? And the answer is yes, I am. So I'm on the right track. And now I can pick up my calculator, or in this case, open it up. Put in the numbers, hit the magic button, and this is the number we get. Now, on test 3, like test 1 and 2, it will say, please use proper significant figures for all calculated answers. So what should the answer be? If you write that down, I'll take off a point and put the letters SF, meaning significant figures. It's wrong. 3 significant figures. I'm in my run again. 3 significant figures, exact number. When you're multiplying, dividing, you have the same number of significant figures in your answers. The number that has the lowest significant, 3 exact number. This doesn't play a role. How do you round that off to 3? You keep the 1, keep the 9. 6 is the last significant. The round off number is 8. That is, hopefully you agree, 5 or higher. Therefore, I drop all that, and the answer is 1.97 moles. So if I need 9.7 moles of a solution, HCl in a solution, I measure out 525 milliliters, which is not hard. It's easier than weighing it, than dissolving it and making up a solution. And this is an important problem. I'll do another one in a second, but let's go out into the real world. This is something I want to show you. When we were making up these solutions, usually they're 1 liter or 500 mil or something like that. And this is called a volumetric flask. A volumetric flask is made just specifically and only to make different molarity solution. This one is to make a final volume of 250. And if you look right here, there's a line. And when you put in the solid and then fill it with, say, water or whatever your solvent, you have the meniscus right to that line. And the accuracy of this one right here is plus or minus 0.12 milliliters. They're very accurate. And most volumetric come in different sizes. I have a collection at home. I've got these cute tiny ones, 1 milliliter and 5 milliliter. Oh, they're so cute. Now you know these are chemists. Anyways, here's a collection of them. Let's see, we'll open up. Nah, this is there. And if you look here, you have a 2 liter, a 1 liter. And this looks like it's probably a 10 milliliter. And the ones I have are even smaller, aren't they cute? And the biggest one I've ever seen is a 5 liter. Ooh, that was huge. And it's a way of making up different molarity solutions. Friday in the lab, I'll see if I can grab one from the stockroom to show you. I like volumetric flasks. They're cute. All right, let's do another problem. On test 3, there'll be important information. You'll have, remember, molarity, capital M, equals moles solute per 1,000 milliliters. Why don't you try this one? Set it up and do it on your own. I'm going to let you do that first, then I'll show you how many moles sodium chloride are in 371.1 milliliters of a 4.711 capital M NaCl solution. Go. Wow, time flies when you're having fun with solutions and molarity. And don't forget, if you ever want an instant replay of Dr. White's lectures, they're on YouTube, because I'm a YouTube star. Not really. When I will become a YouTube star, I'll let you do selfies with me. If you don't have a calculator, just set it up like if you were doing it on a test. Quick reminder, Friday I'll be going through the gas law problems, so please try them before Friday. And if you have any questions, feel free to ask. So I haven't said in a while, but it's always true in my world. There's no such thing as a dumb question.
Which problems did you say?
What?
Which problems did you say? Which problems did you say?
The gas problem.
Thank you.
For those who didn't hear me, I'll repeat again. Friday, we'll do the gas law problems, like the big one, P equal MT, my favorite. All right, I think everybody's done. Let's get it and do this. Let's get a clean board first. And the question is, what are we being asked to find? If you look here, it says how many moles sodium chloride. So we're trying to find moles sodium chloride. What are we given? Well, we have 375.1 milliliters of a solution. And what do we have? We have this number, 4.711. Then we have this capital M NaCl. And the first thing I'm going to do is ask myself, what does that mean? And as soon as you see capital M, it means moles of solute per 1,000 milliliters. And what this really means is 4.711 moles sodium chloride per 1,000 milliliters of solution. And now I have this number to start with, so I'm going to start with that. And if I could convert this in one, using a ratio, in one step, what units am I trying to get to? Well, I took the time to figure out it's moles of sodium chloride. Everybody knows what time it is. It's time to use your good buddy, your good friend, unit analysis. By the way, is anybody keeping count? I'm still going for the Guinness Book of World Record. Most times saying that in a semester. All right, unit analysis tells us what we're trying to get to. Goes on top of the ratio. Whatever we're trying to get rid of, I don't want milliliters in my final answer, goes underneath the ratio. Where do I find those numbers? I took the time to realize that this, capital M, molarity, moles sodium chloride per 1,000 milliliters, and therefore 4.711 per 1,000 milliliters, 4.71 moles of sodium chloride. Notice milliliters divided by milliliters cancels out. I'm left with moles of sodium chloride. I'm on the right track. So now I'm going to go to my calculator. And it gives me this number. And remember on test 3, they'll say please use proper significant figures. This is an exact number. Does not play a role in the calculation. 4 significant, 4. My answer should be 4. How do I round that off to 4 significant figures? Keep the 1, keep the 7, keep the 6, keep the 7, and the 1 to round off, 0. I hope you all agree is 4 or less. And therefore, I get 1.767 moles of sodium chloride per, if I did my math correctly, let's check, because once in a while even Dr. White messes up. 375.1, 4.7, I did it right. And that's one way of doing molarity. Now, let's get back to my slide. Now, let's look at number 3, and we'll come back to 2 and 4 on Monday. Now let's do a different one instead. All right, let me erase this. Haste makes waste. All right, let's take a look at this type of problem. How many milliliters of a 4.55 capital M NA solution, that's wrong. Tell you why I'm racing. We'll do this, pick it up on Monday. Sorry about that. I was trying to get in. I'm going to let you out a whole 2 minutes early. Don't tell anybody. Wait, I'm on the camera. I'll have it down. So with that, I'll see you on Friday. Don't forget, be on time.